we're looking at a region in the first quadrant enclosed by the graphs of y equals e to the 2x, x equals 1 in the coordinate axes. That's going to be rotated around the y-axis, and we want to know what the volume of this solid is going to be. All right, so let's draw the figure. Something along these lines. Alright, so x equals 1. Now we're spinning it around the y-axis. Alright, so we get into a little bit of a dicey situation here because we have two distinct regions. One, if I go from 0 to 1, that's more of a disk method type situation because we're taking rectangles that have constant length and they're uninterrupted between the axis of revolution and the outer extreme of the bounded area. So each one of these rectangles, if I bring it in, it's going to be a little messy the way I mean, you've seen my drawing abilities, so you're not surprised by now. But, and really we don't need all of this because it's bounded by the axis. But if I draw that disk, kinda. Again, that's just a half disk. But as it works its way through the bounded region from 0 to 1, it's gonna be a disk method situation. Alright, so we don't have to go too crazy there. That's good news. Alright. Now, alternatively, you could use just the volume of a cylinder formula. Alright, pi r squared h. But I'll use the disk method just to kind of review that concept and kind of show you how it all goes together. Alright, so that's going to be the integral over the interval of 0 to 1, pi r squared with the radius being 1, so 1 squared, the thickness is associated with y, so dy. Alright, so now we can crunch this in the calculator, but we know that the antiderivative of a constant is just the constant multiplied by the difference between the bounds, so it's just going to be a 1 times pi, which is pi. Alright, so that takes care of that piece. Now this other part is going to get us all the way up to this location. I'm going to make it dashed. That location is what you would get if you evaluated the y equation for an x value of 1. Alright, plug in a 1 for x, and we're looking at e to the 2 times 1, which is e to the second power. So I now know that if I want to find the volume of this piece spun around the y-axis, that I'm going to need to figure out the outer radius, which isn't much of a challenge because we kind of already know that. Let me just get a different color here. So my outer radius, which I'll call capital R, and my inner radius, let's go with an orange. and that's going to be a lowercase r. All right. So the outer radius, that's easy because again, that's the known constant value of 1. So we're going to have a pi over the interval of 1 to e squared. The capital R squared is a 1 minus the lowercase r squared. Right? The lowercase r squared, well, that's a distance away from the y-axis. So that's going to be x. All right, so r is going to be equal to x. And so we would need to solve for that. Now we know the thickness here is going to be a dy. All right, so that's pretty consistent. But if I solve this for x in terms of y, so I have y equals e to the negative 2x. I would take the log of both sides. Ln of y is equal to ln of e to the negative 2x. So ln of y is equal to negative 2x ln of e. Ln of e goes to 1. So we're talking negative 1/2 ln of y is equal to x. All right. So that's what's getting squared over here. And subtracted from the 1 squared dy. All right. Add that to the volume that we've already computed, and we'll have what we need. All right. So, you take a quick glance to see if it's something that you may be willing to try to do by hand, with the idea being that, there's not many instances in which people are going to be interested in doing that. So right to the calculator we go. All right, so Math 9 from, well, you know what, let me put the pi in there first. From a 1 to an e squared. Second ln brings up e to a power. Second division just brings up the e, if you didn't know. So 1 minus, that's this whole thing squared, so negative, I'll write it as 0.5, ln of y. Again, you could use x instead of y if you want, but for consistency, I'm just doing it this way. Consistency with the last video or two that I did. All right, so I think I typed it in all correctly. I'll just do another quick double check. So 1 squared is 1 minus negative 0.5 ln of y, the whole shebang squared. Okay, so we got that, and then we tack on a pi. All right, so 10, this is an approximate 10.0359. And that's going to be approximately 13.177 cubic units. All right, so let's get Desmos into the party here. So I'll do it all in one, well, maybe not one shot, but I'll do it all in one line. All right, so pi integral over the interval of 0 to 1. Open the parens, 1 squared, close the parens, dy plus, right, that gave us a pi, so far so good. Function integral from 1, oh, I forgot the pi, so let me just tuck that in there, from 1 to e squared. And that's 1 squared minus, you know, all that other good stuff. Negative 1.5, so negative 1/2 ln of y, close it up, square it, close up the integrand, slap on a dy, 13.177, which is what we came up with the graphing calculator, the TI that is. Alright, so we're in good shape there. Alright, so number 3, let R be the region in the first quadrant, so first quadrant again, enclosed by the graphs of, this is a cube root function, alright, and x equals 7 and the coordinate axes. So this time I'm going to get a picture with Desmos, so I'll start that off immediately. So I'll write it as f of x though. So this is x plus 1 raised to the 1/3 power. And I got my x equals 7. Now I only want the first quadrant. Coordinate axes, we're rotating around the y-axis. Alright, so I don't want anything to the left of the y-axis or below it. Alright, so I'll just show you a nifty trick here. What we can do is restrict our domain by inserting some squiggly brackets and state the domain, and that domain would be that x is greater than or equal to 0. So I type it, I use the keystrokes, type in a greater than immediately followed by an equals, but if you go to the keyboard you see a greater than or equal to symbol there. And then put in the 0, and you can see that your domain has been restricted. Now, if you really want to get crazy with this, what you can do is restrict your line so that it goes only from the x-axis to the curve itself. In which case, I would be saying that y is starting, well, it's got to be greater than or equal to 0, so 0 is less than or equal to y, and y itself has to be less than or equal to f of x. So we have a nice little restriction going on here. Alright. Now if we really, really want to go and get silly with this, we can restrict this even further by saying that x has got to be between 0 and 7, because really that's where we're maximizing this thing. So I could say 7 greater than or equal, and then have only the relevant region. Alright, so that's kind of nice. You could also, if you want to have some shading, you can do that too. You know, because inequalities take care of shading. Sometimes it's a little iffy when you get into multiple functions. So I find, you know, I just tried it with the f of x. That was a little iffy. It was having a hard time with that. But if you do it with the x and the 7, put a less than or equal to symbol, it'll shade everything to the left of the 7, which is what we would want. All right, so that's the boundary region. That's just fun fact of the day territory, though. We didn't really need that. All right, so this is the bounded region that we're working off of. So what I'll do, you know, the tick marks, or I'm sorry, the grid tends to get in the way, so I turn that off. We would want to have a rectangle on this interval that's spinning around the y-axis. If it was going around the x-axis, it'd be nice and easy. It would be a disk method problem, but it's not going around the x-axis, it's going out around the y-axis. So I would need a rectangle spanning from the y-axis to the vertical line. The problem is, after I get to this location here, which is 0, 1, then it switches over to have a different bounding, just like the previous example. All right. Now, good thing about Desmos, one of the many good things, is that you can get all this information here just by clicking, right? Rather than having to solve or you know some, I'll say advanced techniques in a graphing calculator.
you know, this ends up being a pretty nice way to go. So I'm going to snip this and get it into our notes. All right. Most work was really necessary to get us a diagram. It was really just my way of kind of slipping in some instruction on how to do some of this stuff on Desmos just to make lives a little easier. But if it's not something you're interested in, that's fine too.
All right, so I'm going to draw a horizontal line here going from 0, 1 across to that vertical line. All right, so that's going to
represent us kind of cordoning off the two intervals. The one that we can just do with either the disk method, which we did before, or just pi r squared h. All right, because if I take this whole region, this whole shabiggity bangity boomity bobbity boobity boom here, and spin it around the axis, it's going to have a radius equal to 7 and a height equal to 1. It's going to create a cylinder. All right, so pi times 7 squared times 1 is going to give you 49 pi. So you can do it with the disk method, or you can do it with this formula. All right, it's the other piece that we really care about. So we have this overall length here, which would be our capital R. And then we have the shorter length, which is just going from the axis of revolution, which is the y-axis, to the curve itself. That's the lowercase r. All right, so what we're looking to do is add that result to the 49 pi. All right, so we would be starting at the y value of 2, and again the thicknesses here are going to be in terms of y, so dy. Alright, so I've moved away from drawing the rectangles, and now I'm just drawing line segments with infinitesimal width, alright, just to kind of streamline the process a little bit. But the y values are going from y equals 1 to y equals 2. So over the interval of, well, I don't know why I wrote a 0, 1 to 2, we're going to have a pi r, well, I could put the pi in the front like I've been doing, capital R, which is 7, squared minus lowercase r, which is a horizontal distance away from the y-axis, otherwise known as x. The thickness is in terms of y. I know that y is equal to x plus 1 to the 1/3. If I want to solve it for x in terms of y, I would cube both sides, so y cubed is equal to x plus 1, which makes x equal to y cubed minus 1. Alright, so we're looking at 49 pi plus pi over the integral over the interval of 1 to 2, 49 minus y cubed minus 1 squared dy. And then calculator work. Yeah, I mean, you can simplify it a little bit before going to the calculator if you like, but not necessary. Let me get the 49 pi in there first. 49 pi plus pi, math 9, 1 to 2, 49 minus y squared minus 1, close it up and square it, and y, dy. And that should give us our result, 299.917. And there you go. All right, so over to Desmos. So we have all this information, so, I mean, it gave us a nice looking graph, but then we're doing everything in terms of y, so just got to kind of appreciate it and move on. So 49 pi integral over the interval of 1 to 2. 49, that's the 7 squared, minus the x squared. That was, again, y cubed minus 1. So y cubed minus 1, close it up and square it. Close it up and tack on a dy. And something went wrong. Oh, I forgot the pi. Look at this guy. Forgot the pi. 271.299. All right, well, I still messed something up, so let's take a look. 49 pi. Oh, look at this. Y cubed minus 1. I put a y squared. Noob. 271.299 cubic units. And there it is. And there it is.